this. Yeah, in order to do this, in order to do this, we should, people have done it, right? Working in isotropic coordinates for Schwarzschild, it is easier, it is more direct to apply this method, right? So here, if we change from spherical to cylindrical, there is a z coordinate and we can apply the method. People have done it and obtained sigma, density, surface density, and isotropic pressure of the disk. And here you can see plots of sigma and of pressure. So they are alike the Kuzmin model, which I didn't show, but it is something like this. So this is a way of constructing relativistic disks from monopole solutions, in particular generalizing the Newtonian galactic models. Here I show some biased examples of what has been done in the literature. And I think this is interesting because here we have some papers from the Brazil group, but the thing didn't start in Brazil, right? There's a seminal paper by Jiří Bičak and collaborators on this kind of system. And many other people in Czech Republic work with this kind of system, razor thin disks around black holes. So I apologize if I don't mention some important work, but there's not enough space. But the thing is that you are not, Czech Republic is the perfect place to work with razor thin disks because, well, many of the important contributions to the literature are from this group. In particular, I believe Professor Vladimir Karas is in the audience. I don't know. But let's continue. What about black holes? I didn't talk about black holes yet. I promised in the title that there would be a Schwarzschild black hole. But I didn't do it because one thing, because in general relativity, we don't have a superposition principle. In the way that, in the sense that if we have Poisson's equation and add a monopole plus a disk, the solution, the potential of a monopole plus the potential of a disk will create the system monopole plus disk. In general relativity, the equation for the metric is nonlinear. So what happens is that if I have a black hole solution and a disk solution, and if we add things, we will not obtain a black hole plus disk solution. The system must be solved jointly. The metric will be only one. So if we want to construct a black hole plus disk solution, we have to do something else. We have to, it is not so simple as in Newtonian gravity. And there are many ways to do it. Many ways. And I will talk about one of them, which is the displace, cut, and reflect method that I showed. So I'll be talking mainly about this work. So in order to construct the disk, we must have a seed solution, a solution which will be transformed into the disk. So we got a solution. I didn't write it here, but the solution of Israel and Khan from the 60s, in where they get in Weyl coordinates, and Schwarzschild black holes. Those Schwarzschild black holes, a Schwarzschild black hole in Weyl metric is described by a function psi and a function gamma. Psi satisfies in vacuum Laplace's equation, so it is a good thing. And it turns out that it is described by a bar, like a rod, a bar as the source, right? So we may they superposed a number of bars and then solved the nonlinear equation for gamma, which is the whole point. And then we want to apply the DCR method to this system, which I will show briefly. But first of all, I'll just show that the solution exists, right? This is a generalization of the solution in which we consider not a black hole, but a black hole has length of the bar equals 2m. Here people generalized it for arbitrary lengths. So what we do, we have the solution. It is very simple, the procedure. We have the solution, we have the coordinate z, we apply the method, z going to absolute value of z plus z1 to the here, and then it propagates to everything, and we have the disk. And what does it mean in practice? If we have the origin somewhere, then if we displace to the origin to an appropriate line, we will have a black hole. I mean, we must cut the space-time in the middle of the highest black hole, right? And then if we cut it and throw away the lower part, we get the upper part, which is formed by the field and half of a black hole. The upper half of a black hole, whatever it is, right? We don't know what is the upper half of a black hole. But if we reflect with respect to this plane, the black hole is reconstructed. So here we have the disk, and in the middle we have a black hole. And this is the procedure. This is what the main slide of the talk. We can do it if we have a black hole and some source below, and we construct the disk, right? Here, so just some plots of the disk profiles, and if we change parameters, we can find in particular that a property of good for dealing with accretion disks, which is the angular velocity of these particles, changes with this parameter because of self-gravity. And there are many more people expertised in accretion disks than me to analyze the astrophysics of this. But I would like to finish by, and this is one part of the talk. The other part is 2 slides, right? Which is the stability of those orbits. And I will mention in this, if we have this kind of system, then we know that radial stability of circular orbits is given by the Rayleigh's criterion, this one, or given by the radial epicyclic frequency being positive. Good. But we don't have a vertical epicyclic frequency. We don't have vertical epicyclic frequency in the system, because in this system, the vertical epicyclic frequency would be proportional to a delta distribution. It will not be a good thing. It is not well defined. So what we found is that working with the equations and the Hamiltonian formalism, the sufficient criterion for vertical stability is the validity of the strong energy condition for the disk fluid communion. And this is a generalization of the Newtonian result, right? This is the important thing. And this is it here. I think I don't have the time, but just to say that we also found a way to explain the orbits, the shape of the orbits around the circular, non-equatorial orbits around the circular orbit. And well, and those are the conclusions, which is my idea was to present the method and some applications, and say that in Czech Republic there it is a very good place to work with razor thin disks. Well, so thank you very much for the opportunity, and this is it. So thank you.
Perfect on time. So do you have any questions? Okay.
Hello. There is a kind, hey, hello. There is a kind of superposition principle in general relativity. Is the gravitational decoupling. So maybe, I'm not sure, so maybe you can solve the pure black hole solution and the disk solution and use this kind of superpositions. The name is gravitational decoupling, so maybe it could be useful for you.
I'm sorry, I didn't hear the whole question.
Yeah. It's not a question, it's just information. There is a kind of superposition principle in general relativity. We know there are no superpositions because there are no linear equations, but there is a kind of superposition principle. So by using this approach, the gravitational decoupling, you can solve first the pure black hole solution, which is Schwarzschild. Second, the pure disk solution. And you are going to obtain, of course, two solutions, and a simple combination of these two solutions, maybe if the approach works, in this case, maybe it's going to give you some new information.
Oh, yeah, but really,
okay, just a piece of information. Gravitational decoupling is the approach, so maybe it could be useful for you.
Gravitational decoupling, but is it a property? I should write it. Is it? I didn't know about this property of gravitational decoupling. Is it something general which? Oh, good. So well, we may talk about it. But, so thank you. I'll have a look on gravitational decoupling.
Ronaldo,
hi, Marek. Nice to see you.
Ciao. Ronaldo, have I understood correctly that the matter in your disk is rotating?
No, it's not.
Very good. Then I have no question.
No, yeah. It is a method which is called counter rotation. So the metric is static. So we...
Yes, so it is a static solution with zero total angular momentum.
Yes, it's a static solution, yes.
Yeah, fine.
Good.
Any other questions? Doesn't look like, so we can speaker once again.
Okay.
We will continue with live lectures here from the lecture hall from Opava by Jorge. So the streaming will start again, and we'll see you there. Thank you. Bye.